So, hello everybody, it's my pleasure to present Antoine Song from Berkeley. So last week we gave a nice series of lecture on essential minimal volume. So interested people can look at the video or the note on the platform. And today we'll talk especially on essential minimal volume of Einstein for manifold. So Antoine, please, you can start as you wish.
Thank you for the introduction. So today I would like to talk about the essential minimum volume, which is an invariant that involves the condition that the sectional curvature is bounded. And I would like to give you some estimates for this essential minimum volume in the case of Einstein for manifolds, and also by extension in the case of complex surfaces. So let's get started. My plan is to first give you some motivations and definitions. After going through known results and why I'm interested in that condition that the sectional curvature is bounded, I'm going to give you the main theorem, which is linear bound for the essential minimum volume in terms of the Euler characteristic of your Einstein for manifolds. So then I will give you some elements of proofs for this theorem that uses the thin-thick decomposition of Einstein manifolds, which in itself is an interesting way of thinking of Einstein metrics. Then I will give you an extension of that theorem and an application, if you want, of that theorem to the case of complex surfaces, and that will leads to a linear bound for the essential minimum volume of complex surfaces. And finally, I will give you some questions and conjectures that I thought about. So what is the essential minimum volume? The essential minimum volume is a variant of the minimal volume of Gromov. So what is the minimal volume of a closed smooth manifold M? It's simply given by the infimum of the volume when you impose that the sectional curvature is between -1 and 1. So it's a kind of measure of the complexity of your manifold using the sectional curvature. And what you can do is to look at a variant of this invariant. This is the main thing I'm going to talk about today, which is the following. So given any delta, you can define the delta thick part of your metric G by looking at the points where the injectivity radius is strictly larger than delta. Okay, once you do that, you can define the essential minimum volume as being the limit when delta being positive goes to 0 of the infimum of the volume of the delta thick part, always with respect to that condition that the sectional curvature is bounded by 1. So you see that by definition, the essential minimum volume is going to be bounded by the minimal volume. And so it's a quantity that is easier to bound than the minimal volume, and we're going to bound the essential minimum volume in the case of Einstein manifolds. We're going to ask some questions about the minimal volume. One thing to understand is that the minimal volume and the essential minimum volume are different. They can be arbitrarily different in any dimension, at least 4. Let's see. Right, so Gromov, with previous work of Thurston, Gromov had the idea of studying geometric invariants in order to measure the size of a given topological object. It could be a homological class, it could be, say, a smooth manifold. And in that case, I'm interested in the minimal volume. And more specifically, I'm interested in invariants that actually can be realized as the size of a geometric object. So in the case of the minimal volume, I would like, in fact, to consider a variant of this minimal volume, which is this essential minimum volume. It is a fact that the essential minimum volume is a version of the minimal volume that is actually realized by the volume of a Riemannian manifold that lies in a kind of weak closure of the space of metrics on M with bounded sectional curvature. That's a fact that you can prove using a classical work of Chigger. And so I'm going to just write it down here, not rigorously. The essential minimum volume, you can rewrite it. You can take it as a second definition if you want, as the infimum of the volume of elements. And these elements are certain Riemannian manifolds lying in a kind of weak closure of the space of metrics with bounded sectional curvature. And moreover, again, by Chigger, if, so this essential minimum volume, okay, this is not what I wanted to write. What I wanted to write is that the essential minimum volume is realized. So it is the volume of something, and this something is lying again in that weak closure of the space of metrics with a sectional curvature bounded by 1. So this is the kind of invariant I'm interested in. And in low dimension, the essential minimum volume and the minimal volume are equal. That is a fact. So in dimension 2, it is easy to check because in dimension 2, you have the Gauss-Bonnet formula. And you can check that if you start with a surface of genus gamma, the minimal volume or the essential minimum volume is essentially given by the Euler characteristics. So it's given by the genus of your surface. And moreover, so if gamma is strictly larger than 1, the minimizers, I should say, of the essential minimal volume are exactly the metrics that are in the closure of the space of hyperbolic metrics on your surface. So you have hyperbolic surfaces. The hyperbolic metrics are definitely minimizers for the essential minimum volume, but also you have the generations of those hyperbolic metrics. So these are all contained in this weak closure I talked about. So in dimension 2, because of Gauss-Bonnet, that's fine. Let me give you an example in dimension 3. So in dimension 3, what you can say is that if you start with a closed, oriented, and prime 3 manifold, then the essential minimum volume is equal, so the minimum volume also is equal to the volume of the hyperbolic part of M. So remember that in that case, M is obtained by gluing finite volume hyperbolic metrics with some graph manifold. And the proof of that, you can check that fact by using collapsing theory that I'm going to talk about later, and use the fact that the Yamabe invariant of M is known in that case. So there's a lot of things known in dimension 3, and in particular this Yamabe invariant is known due to the work of Perelman, and it was observed by Anderson. So that is to give you a feel about what the essential minimum volume is and the minimum volume in lower dimension. So in higher dimension, it's hard to compute those invariants. However, surprisingly, Besson-Courtagallo proved that for closed hyperbolic manifold, this the invariant of Gromov called the minimal volume is just the hyperbolic volume. So in that case, you can really compute this invariant. It's given by the hyperbolic volume of your hyperbolic manifold. And in fact, it is also true for the essential minimum volume. So using Chigger, Fukaya, Gromov, you can give a proof that is, I would say, a direct proof of the fact that the essential minimum volume is also equal to the hyperbolic volume of your manifold. Of course, if your manifold is hyperbolic. So these are two cases where one case where you can prove that you can compute the minimum volume or the essential minimum volume. And in general, it's not really possible because it's such a rough invariant using this condition that the sectional curvature is lower bounded and upper bounded. But you can ask the following question. So can you at least estimate the minimum volume or the essential minimum volume of some natural infinite families of manifolds? So this is what we want to do with Einstein manifolds and complex surfaces in dimension 4. All right, so I recalled the definition just in case. So the essential minimum volume is the limit of the infimum of the volume of the delta thick part. And yes, so we chose to study closed Einstein 4 manifold and complex surfaces. What would be great is to estimate their standard minimal volume, and I cannot do that. So I'm going to estimate the essential minimum volume, which is easier to estimate. And okay, some motivation here. So given a delta positive that is small enough, remember that if you're given a metric with bounded sectional curvature, then by the work of Cheeger, the delta thick part, so the part where the injectivity radius is at least delta, is very well understood. So it enjoys some nice compactness properties and finiteness properties. On the other hand, the thin part, it is globally complicated, but at least locally, you can understand it very well due to the collapsing theory of Cheeger, Fukaya, and Gromov. And in particular, the thin part, the delta thin part, carries something that's called an F structure that was defined by Cheeger and Gromov, and also an N structure that generalizes the F structure here. So the N structure was later defined by Cheeger, Fukaya, and Gromov. And the point is that you have a good understanding of the local smooth topology of your manifold. So it means that if you can bound, say, from above the minimum volume or the essential minimum volume, that provides quantitative information on your smooth structure. For example, if you have a bound on the essential minimum volume, that means you can decompose your manifold into two pieces, one piece where locally you have those very strong structures, those N structures, and another piece that has everything bounded by this bound on the essential minimum volume. So other motivations, that's more for Einstein metrics themselves. So previously, results about Einstein metrics often required assumptions on the volume of balls, say non-collapsing conditions, and on the diameter. So you can see the work of, say, Anderson, Cheeger Anderson, and more recently Cheeger Neighbor. It is often useful to require that you have non-collapsing in order to get something that is strong enough. But what we would like to do is to get a result for unbounded families of, say, Einstein 4 manifolds. And so estimating the minimal volume or the essential minimum volume would be a way to say something when you don't have any bounds, say, on the diameter or on the non-collapsing of your metric. Another question, which is due to Kochik, is the following. So he asked if a given topological closed 4 manifold can only carry finitely many smooth structures with an Einstein metric on it. And of course, that is true for all the, there's no counterexample, right? And what I want to say is that because of this very close relationship between the volume when the sectional curvature is bounded and the smooth structure, in some sense, if you can bound the minimal volume, that enables to quantify a version of this question of Kochik for, say, smooth structures modulo F structures. So instead of looking at smooth structures, we're looking at the smooth structure, but you don't care about pieces that carry an F structure or say an N structure. So note that the definition, I didn't give you any definition for F structures, but an F structure is defined purely using smooth differential topology. There's no metric involved. And so this remark is a consequence, again, of the fact that by Cheeger, if you have a bound on the volume of the thick part, the thick part has somehow bounded smooth structure, cannot be too crazy. All right, so these are the motivation, and finally I can give you a statement. So this is the first main result, which says that there's a universal constant, so that given any manifold that has an Einstein metric on it of dimension 4, the essential minimum volume is comparable to the Euler characteristic. So here E is the Euler characteristic. And note that, so the essential minimum volume is defined using metrics and the smooth structure, but here in that particular case, you can bound it by something purely topological. And it's kind of reminiscent of what's happening in dimension 2 for two-dimensional real surfaces, where the essential minimum volume is given by the Euler characteristic. Let's see. So I want to make some comments about this statement. First comment is that I think that it should be true for the minimal volume, but I find it hard to show, and I'm going to try to explain why there's this discrepancy between the essential minimum volume and the minimal volume. Yes, so that should be true. Another thing is that the lower bound here is relatively easy to show. So once you know a bit about the definitions and you know a bit about collapsing theory, then you realize that yes, it is true, that always true. You don't need the Einstein assumption for any manifold. You have this lower bound with okay. In general, you should add the absolute value here, but here, since the Euler characteristic is always non-negative, so you don't need the absolute values. And so the difficult part is to bound from above this this invariant, the essential minimum volume. In other words, you start with an Einstein metric. You want to deform the metric so that it becomes bounded sectional curvature, but also it has a nice bound on the volume of the thick part. This is essentially what you're trying to do. Previously, Cheeger and Neighbor, they showed something that says that if you impose a diameter bound and, more importantly, a non-collapsing condition, then the number of diffeomorphism types of such Einstein form manifolds is finite. So what they prove, maybe I should write more, is something more general. It's a codimension 4 theorem that says that the singular set of non-collapsed Ricci limits is a codimension 4, and in particular, when you use that result in dimension 4, you get this finiteness result. And that's a result that's going to be useful in the proof. So remember here, okay, they need this non-collapsing condition. In our statement, we don't see this, we don't need to assume anything on the non-collapsing, but then we will, in the proof, need to use Cheeger and Neighbor. We'll see why. Theorem, it is very convenient to study so-called thick-thin decomposition of your Einstein metric. And it's going to be a decomposition into two pieces of your metric that is made accordingly to this epsilon. So it is by design. Capturing this epsilon regularity theorem. So what is it? Well, so you start with an Einstein for manifold, and first you fix a volume threshold so that you can define a so-called non-collapsing scale. And the non-collapsing scale is given at any point by taking the supremum of the radius such that the volume of the ball is, when you rescale it, normalize it, is at least V. So V is your threshold. So once you have V, you can define this non-collapsing scale. So it's just a radius that evolves continuously, right? And you can define the thick-thin decomposition per C. So you can write that M is a disjoint union of two parts. So the first part, where you have larger than epsilon, it's simply where on the scale of non-collapsing, so non-collapsing scale, you take the L2 norm of the curvature, you get a number that is strictly larger than epsilon. And the complement set is this other part. So the epsilon is chosen, V is chosen very small, and then you choose the epsilon very, very small compared to the V, so that you can apply the epsilon regularity theorem. So what do I mean by that? The one detail is that if the Ricci curvature is 0, you want to rescale your metric so that it becomes very small, so that the following will be true. You can guarantee that if V is small, and also if epsilon is small compared to V, then around any point in the thin part, so-called thin part of your manifold, the geometry is actually collapsed in the sense of Cheeger-Foucault-Gromov. So it has a small injectivity radius compared to the sectional curvature. So this thin part that we defined simply using L2 norm of the curvature is actually thin in the sense of the sectional curvature, at least locally when you rescale. And so in other words, this thin part is described by, again, these results by Cheeger-Foucault-Gromov in particular. In particular, it carries an N structure. Okay. So by using collapsing theory, and in fact, you need to improve a certain collapsing construction by Cheeger-Gromov, I claim that the proof of the theorem essentially just reduces to showing that the thick part of your manifold carries a metric with bounded sectional curvature and bounded volume. So you want the volume to be upper bounded by the other characteristic. So in other words, in dimension 4, there's this nice thing that if you care about the essential mean volume, you just need to care about the delta thick part for some delta fixed dimensional constant. Once you can evaluate the volume of the delta thick part, you evaluate the essential the minimal volume. So that is true in dimension 4. That is a claim. But how do you work on this maybe before that, let me make this remark a little bit more clear. So remember, the essential mean volume, a priori, you need to take a limit of delta thick parts, right? A priori, you need to know something about the volume of the delta thick part for any delta going. So remember here, it's delta thick in the sense of sectional curvature, so where the injectivity radius is larger than delta. But in this, because collapsing theory plays nicely with dimension 3, you show that you only need to, say, evaluate this number for some fixed delta. So in dimension 4, I'm saying that if you can construct a metric such that the thick part has volume, say, less than T, then the essential middle volume is already less than a constant times T. So the constant is a universal constant. So in dimension 4, there exists such a delta. And it's probably not true in higher dimensions. So that's why now the job is to look at this thick part, so thick part in the thick thin decomposition of your Einstein metric. So the idea is to localize to your neighbor. So you have this thick part, it's defined using some condition using the non-collapsing scale. So what you can do is to try to use Shiga-Neighbor's results, and then you patch the estimates together. Remember what Shiga-Neighbor is saying is that if on the already non-collapsed, then actually the diffeomorphism type of such thing is finite, at least inside, say, a smaller ball. Let's say p1/2 is bounded. It belongs to a finite list. That depends on the non-collapsing threshold B. So let me go back to this definition of the thick thin decomposition, just to show you, convince you that Shiga-Neighbor is going to be useful. So when you look at the scale of non-collapsing, you really have the good thing about both worlds. So at the same time, you're collapsed because the volume when normalized is, say, equal to V, essentially, on the scale of non-collapsing. But also, it is, since it's equal to V, it is not too small, so you can apply Shiga-Neighbor. So on bolts with this radius, what do we get if you apply this finiteness result of Shiga-Neighbor? A first step is to find a cover of your thick part with balls such that each ball carries some curvature, and the covering multiplicity of the cover is uniformly bounded. So, okay, you have your manifold, and suppose you can find a cover with balls of radii comparable to the non-collapsing radius, then if the multiplicity is bounded, since you are in the thick part, then each ball, by definition of the thick part, carries some L2 norm of the curvature. All right, so that means since the total L2 norm is bounded by the Euler characteristic, that means the number of balls that you have is bounded linearly by the Euler characteristic. Multiplicity over is then the number of balls in this cover will have to be bounded by a constant times the total L2 norm. So in other words, this is what we want. And once we have that, we need to say, well, in each ball of radius RV, the non-collapsing scale, you can apply Chiger neighbor. That means that you have a total control on the smooth structure in such a ball. And that means in particular that you can put a metric, say, with bounded sectional curvature and uniformly bounded volume. And then you need to take care of how to glue together these metrics. But the claim is that this is possible. But it's the harder part, I think, of the proof. Let's see, do I have time to give some more details? I'm going to continue, and maybe I'm going to come back to this proof to give more details. But the idea is simply you reduce to estimating the size of the thick part of your Einstein manifold, and you try to construct a metric with bounded sectional curvature and bounded volume by applying Chiger neighbor locally. So the difficulty being all these balls might have a different size, and the Bishop-Gromov is not enough to control these in simple terms. So what's interesting then is you can apply this result about Einstein for manifolds to another family, well-studied family of four-dimensional manifolds, complex surfaces. So this is an extension of the previous result, and you can ignore Einstein metrics because we already talked about this. And the theorem says that if you are a complex surface of non-negative Kodaira dimension, then the same is true. So the essential minimal volume is bounded by the Euler characteristic. So you have a rather decent estimate of what the essential minimal volume is. Pretty similar to the two-dimensional case again. And again, I think it's true for the minimal volume, but I don't know how to prove it. So I didn't define what non-negative Kodaira dimension is. I won't, but one example to keep in mind is that if you look at zeros of polynomials, say of degree at least 5, and if it's smooth, then if you are in, okay, a lot of typos today. So in CP3, you look at the zeros of a polynomial of degree at least 5, then you get something that is a surface of Kodaira dimension 2. So it's a surface of general type. And in particular, you have non-negative Kodaira dimension, and that applies. So this is the main family of complex surfaces we're interested in, those which are of general type. I should mention that there were some previous work of Lebrun about some other kinds of minimal volumes. So Lebrun studied minimal volumes involving the scalar curvature and the Ricci curvature. And in these cases, because by his use of Seiberg-Witten, he can actually compute certain of these invariants involving the scalar curvature or the Ricci curvature. Use a Seiberg-Witten to compute. The minimal volume with respect to certain scalar curvature or Ricci curvature, and it's more integral versions of the minimal volume. So it's a little bit different, and the techniques are completely different. So what about this term? What you can say is that the main idea of the proof then is to use the following generalization of the theorem of Aubin and Yao, which is due to Kobayashi and Tsuji. Remember, Aubin and Yao tells you that if you have a surface of complex surface with, say, negative first-gen class, then you get automatically a smooth Einstein metric. What is true in general, say for surfaces of general type, so that is a lot more surfaces, is that you take any surface of general type, then after maybe collapsing some spheres, you get a Kähler-Einstein metric. So by collapsing some spheres, I mean, first, for example, you don't want to have -1 curves, so spheres that intersect with number -1, and you also want to contract spheres, so the spheres with self-intersection -2. So this is a fact, and what it means for us is that even though in general surfaces of general type do not admit an Einstein metric, at least coming from complex geometry, at least they, once you remove certain parts of your surface, you get an orbifold metric that is Einstein, and then you can try to apply the previous theorem. So let me write down something more here. Or so you start with S0 of general type, and you can find an S1 which cannot be decomposed as a connected sum of a complex surface and CP2 bar. Okay, once you do that, you have this S1. What you do is you contract certain -2 curves inside S1 to points, say P1 to PK, and you have an orbifold metric on this new orbifold where you contracted these -2 curves. So get so S2 is this orbifold, and it forgets a little bit about S1, but you can recover S1 by the following procedure. S2 carries a Kähler-Einstein orbifold metric. Then what you can do is you glue around P1 to PK, you glue certain Ricci flat metrics on a complete Ricci flat matrix, the so-called ALE spaces. So then to S1. Complete matrix. The geometric picture being that, okay, near the orderfold singularity, you're a quotient of R4. And those Ricci flat complete metrics at infinity, they're all also quotient of R4, and this is how you glue them. And then you recover S1. So these remarks are just to say that you can adapt, say, the proof of the main theorem about Einstein four manifolds to get some information about complex surfaces, the sectional curvature of complex surfaces. And actually, I'm going to end very early. So let me say a bit about the questions. Again, the result, I think they should be true for the minimum volume, but then a proof for the minimum volume would require some better understanding of the collapsing part. So this thin part of M that is covered by N structures. So right now, you know that it can be collapsed. So bounded sectional curvature and injectivity radius going to 0, but you don't know if you can collapse it so that the volume, you don't know if you can bound the volume of that guy, even though you can collapse it. So you know how to construct metrics with bounded sectional curvature, injectivity radius going to 0. But that doesn't mean that the volume is going to 0. To bound the volume. Because in order to bound the minimum volume, you want to bound the volume of this thin part given a bounded sectional curvature metric. So that is the first remark. The second remark is more about finding new obstructions to these invariants. So,
there's a question in the chat.
Yes, I just saw this. So I don't know of a general restriction. So one obvious restriction is that the L2 norm of the curvature, this is nicely bounded by the other characteristics. So you might hope that, okay, you know the collapse geometry, and you know that the L2 norm of the full curvature tensor is well bounded, then probably you should get a metric with bounded sectional curvature and the same bound. But when you think about that, then actually you don't know enough about the about the collapsing part. So I don't think I know a general restriction about this thin part, especially when you're not in complex geometry. When you are in complex geometry, you can look at, for example, at least Ricci flat metrics, and there are some recent results about the structure of the collapsed part of, say, Ricci flat four-dimensional manifold, like Euler surface. Yes, so the last point I wanted to emphasize is that there are, unfortunately, very few lower bounds, topological lower bounds for the volume of Einstein four manifolds or the volume of manifolds with bounded sectional curvature. So when I say lower bound for the volume of Einstein four manifolds, I'm actually thinking of topological obstructions to the existence of Einstein metrics. And in each case, there are essentially just two kinds of obstructions. One is given by characteristic numbers. So for characters number, for instance, you can bound the minimal volume or the essential minimum volume by the Euler characteristic. We already saw that. But more generally, the minimal volume can be lower bounded by any other characteristic number, which is if it is non-zero. And that's a very simple argument using the fact that your character's number, you can write it as an integral of a polynomial in the curvature. So that's simple. And the other obstruction is given by something like this. The simplicial volume. So that's for the volume of manifold with sectional curvature. And very similarly for the obstruction as concerning the Einstein for manifolds, it's really the same. So we have an obstruction using characteristic numbers, and that is due to Hitching and Thorpe. You have an obstruction, let me remind it. So it's either 2/3 or 2/2 times the signature. So we have the signature. So this inequality holds if M carries an Einstein metric, M being of dimension 4. So that's a restriction, right? Because it's topologically, there are a lot of manifolds not satisfying this bound. And on the other hand, you also have this bound using the simplicial volume. Again, the simplicial volume is this topological quantity that was defined by Hermann. And you have these similarities, and in both cases, you really lack a good understanding of what obstructs the existence of such and such. So I'd like to propose something that might be a new topological obstruction, which is very simple to state. It's the following. So for any, say, closed smooth Fourier manifold, and for any genus gamma, what I want to say is that, say, the essential minimum volume, and in particular the minimal volume of this particular manifold is lower bounded in terms of the genus. So this manifold is the connected sum of n with the product of S2 with a surface of genus gamma. Note that because of an Euler characteristic computation, it is clear that you have this. That is something that is clear. But the point is that the Euler characteristic should not be the main point. It should not be the reason why this manifold cannot be collapsed. So this is what I think is true. And once you have that, then because of the theorem that I mentioned in the beginning for Einstein for manifold, you would get an obstruction, topological obstruction for the existence of Einstein metrics. Right. So by the first theorem, that would give some obstructions. I think I'm done. So thank you for your attention.
Thank you. Is there a question?
May I ask?
Yes.
So what are the manifolds where the minimal volume is 0? Can you control them? So the closed manifolds, all the essential minimal volumes. So is there a big difference for that?
Yes. So the question is hard. It is easy for the essential minimal volume. So let me write down a statement, which is you have a nice characterization of when the essential minimal volume is 0. It's exactly when you have this structure by Shiger-Gromov, say, there exists an F structure, a so-called F structure. The F structure being defined locally, but it gives you a complete smooth topological characterization of when the essential minimal volume is 0. However, this is not true for the minimal volume. People do not have a good condition that implies and is equivalent to the fact that the minimal volume is 0. And to give you an idea of how ignorant people are about these questions, so there's this gap conjecture of Gromov about the minimal volume that says that if the minimal volume of a manifold is smaller than the dimensional constant, it should be 0. And that's not known in any dimension at least 5. Right. And a remark is that once you have an F structure like this, here your Euler characteristic is 0. But maybe other characteristic numbers are not 0.
In the second line, is there an application? So minimal of m equals 0 implies that there are F structure.
Oh, so yes. So at least, okay. So thank you for I didn't mention it, but at least, yeah, as you said, there is one direction that is known. But the thing is that this is not the right condition because the other direction is known to be false.
Is there any question?
If we consider a closed Kähler manifold and blew up along the subvariety, what's the relationship between the two manifolds, minimal volumes?
Yeah. So if you, let's see, let's see what is known about comparing.
We consider some P3 surface and blow up at some points.
Right. So if you blow up, that's topologically a connected sum, and you know that if you make a connected sum, you have some kind of linear bound. It's not optimal. So, for example, if you look at the minimal volume of say of you have this natural bound that you would expect, which is the sum. So sum. And you have some error term. So yeah, some. So for example, in your question, if you do a finite number of blowups, then the minimal volume of the result is less than the minimal volume of your surface plus the number of times blow up times a constant. along more complicated varieties, subvarieties, I do not know what that gives. I do not know. Probably you would get something like this, like an upper bound. But I didn't make any computation.
Thank you.
Are there other questions? No, so thanks.
Yes, maybe.
Yes.
Are there example of Einstein manifold for which the essential minimal volume is not achieved by an Einstein metric or something like that? Or maybe no example are known. I don't know.
So when you look at, for example, the theorem over and Yao, that gives you a Euler-Einstein metric, and usually you don't have good, say, sectional curvature bounds on such a metric. So I don't see any reason why the minimum volume would be achieved by a rescaling of such a metric, but I cannot prove that it's not the case. Simply that Ricci constant, that gives you a lot of metrics, and in general, the sectional curvature is not upper bounded.
Yeah. Okay, thank you.
Okay, so there is no more question. So thank you, Antoine, for the talk and for waking up early for us.
Thank you.
Connexion.